All right, welcome to the 24th video in Introduction to Quantum Field Theory. And this one will be on solutions to the Maxwell equation. Essentially, everything in this video or everything for the Maxwell equation is the same as the Procol equation, just without mass. But there are some subtleties due to something called gauge symmetry. So first off, let's just write what the field equation or what the equation of motion is. It's just this. And you can rewrite this in terms of the gauge field equal to 0. And this form comes about because of the Lorentz condition, which says that the dot, or the, what do you call it? The divergence of the gauge field is 0. So let's talk a little bit about gauge symmetry. So suppose there exists a scalar field. So a scalar field, this is scalar. Let's say we don't know whether it's real or complex, it's just a scalar field. So suppose that it exists such that the gauge field, a mu of x mu, maps to a prime mu of x mu, which is equal to a mu of x mu plus the gradient of this scalar field. If we apply this transformation to the if we apply this transformation right here to the Lagrangian density, we will find that the Lagrangian is unchanged. So let's go back up to a few lessons ago where we were dealing with the Lagrangian. So yes, we have this right here as our Lagrangian. And because this is the Maxwell equation, not the Procol equation, m is 0, so this term disappears. Am I missing a 1/2? No, I'm not. I'm good. Okay, just going crazy. So we have the Lagrangian density. Now we're going to apply this transformation to it, this gauge transformation. So this implies that the transformed Lagrangian is going to be exactly the same thing, except there are these primes now. And let's expand let's expand this out. Minus, then we get partial mu of a plus partial mu of a nu plus partial nu of the scalar field, partial mu of a nu plus partial mu of the scalar field minus partial mu of a a nu plus partial nu of the scalar field, then partial nu a mu plus partial mu of the scalar field. Cutting it a little close there with the room. But this is because we use different indices here. So this is a mu But if we had a nu here, then this would be nu, nu. So we can say that a prime nu is a nu partial nu. So we can just plug those in. So we've now mapped to it. So now we get to have the fun job of expanding this and seeing what happens. So I'm going to expand first this product into parentheses, this product into parentheses. Same for these two. So negative. So let's go here. Partial mu a nu plus partial mu partial nu b. Then partial mu a nu plus partial mu partial nu b minus partial mu a nu plus partial nu phi. Oh, I just rewrote the thing from last section. Okay, that's not what I wanted to do. Plus partial mu partial nu phi. Then I'm out of room, so move it over. Partial nu a mu plus partial mu phi. There we go. So now I'm going to expand all these terms. I'm going to put all the terms that look the same as the original Lagrangian. I'm going to put all the terms that look like this to the left, and all the new terms will be to the right. So negative we get partial mu a nu partial mu a nu minus partial mu a nu partial mu a mu. That comes from this term, comes from this, and this term comes from this and this multiplication. So now we get to add all the extra stuff where we're considering this term, or where we consider cross terms, and then these. So plus partial mu a nu partial mu partial nu phi plus partial mu partial nu phi partial mu a nu plus partial mu partial nu phi partial mu partial nu phi. Then minus, so now we're in these terms, partial mu a nu partial nu partial mu phi minus partial mu partial nu phi partial nu a mu plus, or sorry, minus partial mu partial nu phi partial mu partial nu phi. So we get this. Well, we can actually, and I'll now write in a different color. We can swap indices here because this is a scalar, so that allows us to swap indices here, which means these are going to now cancel. Here we can relabel indices because this is independent actually of this. So we can relabel indices rather than swap. So we get partial mu, partial nu. And here we have these two things. We can just swap, what do you call it? move these. I'll just do this. Mu, 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 mu. And so these terms actually all cancel out. So we end up with negative partial mu a nu partial mu a nu minus partial mu a nu partial nu a mu, which is the original Lagrangian. So we've now just proven that under a gauge transformation, the Lagrangian stays the same. So this is called gauge symmetry, and it's a feature of massless fields where the mass is equal to 0. Now let's also briefly recall just take a look at the dispersion relation. So the dispersion relation for massless gauge fields. Normally it's equal to m squared, but m is 0, so it's equal to 0. So if a field excitation propagates in the z direction, then k mu is equal to k naught minus k 3 k3, which is equal to 0. So that implies that k naught is equal to k3. So for massless gauge fields, you get these properties that the wave vectors are nilpotent or light-like. You can see that it squares to 0 because, or well, it squares to 0 here, but the squaring to 0 implies that the components are equal. And we've seen this a few times in the stuff we've done before and also in geometric algebra, so this should be a familiar concept.